Hello, and welcome to our journey through humanity's ultimate survival challenge. Tonight, we are not just talking about another adventure story or science fiction scenario, but a very real possibility that could face any future space traveler. Something extraordinary and terrifying awaits us just 250,000 miles above the moon, where survival depends entirely on preparation, knowledge, and split second decisions in an environment that offers no forgiveness for mistakes. This lunar wasteland is not merely another destination to explore. Unlike any environment on Earth, the moon presents challenges so extreme that a single equipment failure, a torn spacesuit, or a wrong decision could mean the difference between life and death in minutes. What makes lunar survival even more daunting isn't just the lack of air, water, or warmth, but the countless invisible dangers, from radiation bombardment to temperature swings of 300 degrees, from razor-sharp dust that can destroy equipment to the psychological terror of complete isolation in an utterly silent world. Before we explore these life or death scenarios, imagine yourself in this moment, safely here on Earth, breathing without thought, unaware of how precious and fragile the conditions are that keep you alive every second. If survival stories and emergency preparedness capture your interest, consider subscribing or liking this program. It helps more curious minds learn crucial knowledge and prepares us all to face the extraordinary challenges that space exploration brings. Now, take a moment. Let your mind prepare to grasp what it truly means to be utterly alone on a world that wants to kill you, where every breath must be earned, every movement calculated, and every decision could be your last. This is the beginning of your Moon Survival Guide, where knowledge becomes the difference between returning home and becoming another silent monument on an airless world. The human body draws its next breath without conscious thought, an automatic process refined through millions of years of evolution on Earth. Yet in this moment, suspended in the strange silence of the lunar landscape, each inhalation becomes a calculated choice between survival and panic. Your spaceship rests motionless behind you, its hull scarred from an unplanned descent through the moon's tenuous atmosphere. The familiar hum of life support systems has fallen silent, replaced by something far more unsettling, the complete absence of sound that only occurs in true vacuum. Through your helmet's faceplate, the alien world stretches endlessly before you, bathed in harsh sunlight that creates shadows so deep they appear to swallow light itself. The first sensation that strikes most people in this situation is not fear, but disorientation. Your inner ear, accustomed to Earth's gravitational pull, struggles to make sense of movements that feel simultaneously sluggish and weightless. Each step launches you higher than expected, causing your body to compensate with exaggerated movements that waste precious energy. Scientists who have studied low-gravity environments report that this adjustment period typically lasts between 3 and 6 hours, during which physical coordination gradually improves as the brain recalibrates its expectations. Your oxygen supply becomes the immediate focus of attention. The portable life support system, strapped to your back, contains approximately 8 hours of breathable air under normal conditions, but stress and physical exertion can reduce this duration significantly. During emergency situations, oxygen consumption can increase by 40 to 60% above resting levels as your body responds to elevated heart rate and deeper breathing patterns. This biological response, while natural, represents your first critical challenge in lunar survival. Understanding your breathing becomes essential for extending your life support duration. Emergency protocols developed by space agencies recommend adopting controlled breathing techniques similar to those used by deep-sea divers. By consciously slowing your respiratory rate and avoiding shallow, rapid breaths that characterize panic responses, you can reduce oxygen consumption by up to 20%. This technique requires practice and mental discipline, particularly when faced with the overwhelming psychological impact of finding yourself alone on another world. The moon's gravity, measuring 1/6 of Earth's pull, creates unexpected challenges for human physiology during the initial adaptation period. Blood circulation patterns change as the cardiovascular system adjusts to reduced gravitational stress, potentially causing lightheadedness or spatial disorientation. Many astronauts report experiencing a sensation described as lunar vertigo during their first hours on the surface, where the brain struggles to establish a reliable sense of up and down in the altered gravitational environment. Your immediate survival depends on establishing clear priorities among available resources. Medical experts studying survival scenarios rank oxygen as the primary concern, followed closely by thermal regulation, water consumption, and finally food supplies. This hierarchy reflects the human body's tolerance limits under extreme conditions. Consciousness can be lost within minutes of oxygen deprivation, while starvation typically requires weeks to become life-threatening. Emergency signaling represents another crucial consideration during these first hours. The equipment scattered around your landing site may include reflective materials, radio components, or electronic devices capable of transmitting distress signals toward Earth. Creating visual signals using polished metal surfaces or spacecraft components can generate light flashes visible to orbital reconnaissance satellites, though the effectiveness depends on proper positioning relative to the sun's angle and Earth's location in the lunar sky. The psychological impact of witnessing Earth from the lunar surface cannot be understated in survival planning. That small blue sphere hanging in the black sky represents every human relationship, every familiar environment, and every comfortable assumption about reality that you have ever known. This perspective, termed the overview effect by researchers, often triggers profound emotional responses that can either motivate survival efforts or induce overwhelming despair. Managing these psychological reactions becomes as important as managing physical resources. Temperature regulation emerges as an immediate concern once the adrenaline of landing subsides. The moon's surface experiences temperature variations exceeding 400 degrees Celsius between day and night cycles. During lunar day, surface temperatures can reach 127 degrees Celsius, while nighttime temperatures plummet to minus 173 degrees Celsius. Your pressure suit provides some thermal protection, but prolonged exposure to these extremes will overwhelm any portable life support system. Understanding your body's thermal regulation becomes essential for energy conservation. The human body maintains core temperature through metabolic heat production and behavioral adjustments, both of which consume additional oxygen and energy reserves. Seeking shelter from direct sunlight during day periods and finding thermal mass for nighttime warmth can significantly extend your survival duration while reducing the metabolic burden on your life support systems. Water requirements shift dramatically in the lunar environment despite the absence of atmospheric humidity. The stress of emergency survival, combined with altered gravitational effects on circulation, actually increases hydration needs above terrestrial levels. Space medicine research indicates that astronauts require approximately 3 to 4 liters of water daily to maintain optimal physical and cognitive performance, with additional reserves needed for emergency situations. Your survival timeline depends on managing these interconnected challenges simultaneously rather than addressing them sequentially. Oxygen consumption affects thermal regulation, which influences water requirements, which impacts cognitive function needed for decision making. Emergency survival protocols recommend creating written checklists during the initial hours when mental clarity remains high, establishing procedures for resource management that can be followed even as fatigue and stress accumulate. The landscape surrounding you contains both hazards and potential resources that become apparent only through careful observation. Crater walls may provide shelter from radiation and temperature extremes, while permanently shadowed regions could contain water ice deposits accessible through improvised extraction methods. Learning to read these geological features requires abandoning terrestrial assumptions about terrain navigation and embracing the unique characteristics of lunar geography. Communication with Earth presents additional challenges that affect psychological well-being during the critical first hours. Radio signals require approximately 1 3/10 seconds to travel each direction between Earth and Moon, creating noticeable delays in conversation that disrupt normal communication patterns. This delay, combined with potential equipment damage from your unplanned landing, may leave you completely isolated from outside assistance for extended periods. Your mental state during these initial hours significantly influences long-term survival prospects. Maintaining structured thinking processes and avoiding panic responses requires conscious effort when faced with an environment that contradicts every instinctive survival mechanism developed through human evolution. Research on extreme survival situations demonstrates that individuals who establish routine procedures and maintain task-focused thinking patterns show significantly higher survival rates than those who allow emotional responses to dominate decision-making. The silence of the lunar environment becomes both ally and enemy in survival planning. Without atmospheric sound transmission, you cannot hear approaching hazards such as micrometeorite impacts or equipment failures until they create vibrations through direct contact. However, the same silence eliminates acoustic distractions that might impair concentration during critical problem-solving tasks. As your first hour on the lunar surface concludes, the initial shock begins yielding to systematic assessment of resources and challenges. Your body continues adapting to reduced gravity, while your mind catalogs available equipment and potential shelter locations. The Earth hangs motionless in the star-filled sky above, a reminder that survival depends not on rescue from above, but on your ability to transform an alien world into a temporary home until help can arrive. Each breath drawn through your life support system represents both a victory against the hostile environment and a step closer to resource depletion. The mathematics of survival become inescapable, mealess oxygen reserves diminishing with each respiratory cycle, battery power declining with each passing minute, water supplies finite against an indefinite timeline. Yet within these constraints lies the framework for methodical survival planning that can extend your presence on this silent world far beyond initial estimates. Your first hours on the moon establish patterns that will determine whether you become another casualty of space exploration or a testament to human adaptability in the face of impossible circumstances. The choices made during this critical adaptation period S, how carefully you manage breathing, how efficiently you assess resources, how effectively you control psychological responses, create the foundation upon which extended survival becomes possible. The lunar landscape stretches endlessly in all directions, unchanged by your presence, yet somehow transformed by your perspective. You stand at the intersection of human ambition and cosmic indifference, carrying within your pressure suit all the knowledge and determination that millions of years of evolution can provide. Your next breath, and all those that follow, will determine whether this alien world becomes your temporary refuge or your final destination. What would happen if you found yourself standing in a world where shadows hold more secrets than sunlight? The lunar landscape spreads before you like a frozen ocean of gray powder and sharp-edged stones, carved by 4.5 billion years of cosmic bombardment into patterns that seem both alien and strangely familiar. Understanding this terrain becomes your lifeline, quite literally, as every ridge and crater represents either sanctuary or hazard in your quest for survival. The moon's surface tells stories written in impact craters, lava flows, and dust accumulations that stretch back to the formation of our solar system. Learning to read these geological narratives can mean the difference between finding life-sustaining shelter and wandering into lethal exposure. The dust beneath your feet bears little resemblance to earthly soil. Lunar regolith consists of razor-sharp glass fragments and pulverized rock created by billions of years of meteorite impacts. Each particle maintains angular edges that never experience the weathering effects of wind or water, creating a surface that adheres to everything it touches through electrostatic attraction. This fine material penetrates mechanical joints, clogs filtration systems, and poses serious health risks if inhaled, yet it also provides clues about safe passage and potential resources. Crater formations dominate the lunar landscape, ranging from microscopic pits to massive depressions spanning hundreds of kilometers. These impact structures create natural shelters that can protect you from radiation exposure and extreme temperature variations. The rim walls of larger craters often rise several meters above the surrounding terrain, casting shadows that persist for hours or even days, depending on the sun's position and the moon's rotational cycle. Identifying potentially useful craters requires understanding their basic structure and formation. Fresh impacts create sharp-rimmed depressions with central peaks and terraced walls, while older craters appear more rounded due to ongoing bombardment and the gradual slumping of loose material. The age of a crater influences its suitability, as shelter's newer formations provide clearer structural integrity, while ancient impacts may have accumulated water ice deposits in permanently shadowed regions. The play of light and shadow across the lunar surface creates navigation opportunities unavailable on Earth. Without atmospheric scattering to soften sunlight, shadows appear absolutely black, while illuminated areas shine with brilliant intensity. The stark contrast allows you to determine the sun's position with precision, establishing a reliable reference point for maintaining direction across the featureless terrain. Shadow patterns also reveal information about underlying topography that might not be visible from ground level. Subtle variations in shadow length and direction indicate slopes, ridges, and depressions that could provide shelter or present obstacles to movement. Experienced lunar observers learn to interpret these light patterns like topographic maps, reading elevation changes and surface features through careful observation of illumination boundaries. The Earth's position in the lunar sky provides another crucial navigation reference that remains relatively fixed due to tidal locking. From any given location on the moon's near side, Earth appears to hover in nearly the same position throughout the lunar day-night cycle, moving only slightly due to orbital mechanics and the moon's slight wobbling motion called libration. This celestial landmark serves as a constant directional reference point, unlike the sun, which travels across the sky over the course of 14 Earth days. Permanently shadowed regions represent some of the moon's most valuable yet dangerous territories for survival purposes. These areas, found primarily near the lunar poles and in deep crater floors, never receive direct sunlight and maintain temperatures below -200 degrees Celsius. While these frigid conditions make them inhospitable for immediate shelter, they may contain water ice deposits accumulated over billions of years from comet impacts and solar wind interactions. Recognizing potentially ice-bearing terrain requires understanding the geometry of shadow formation. Areas that remain in darkness throughout the moon's rotational cycle typically occur where crater walls or mountain ridges block sunlight at all possible angles. These regions appear as persistent dark patches that maintain consistent boundaries regardless of the sun's position, distinguishing them from temporarily shadowed areas that experience periodic illumination. Rocky outcroppings and boulder fields scattered across the lunar surface provide both opportunities and hazards for survival planning. Large rocks can serve as windbreaks against solar particle streams and sources of thermal mass for temperature regulation, but they also represent obstacles to movement and potential crushing hazards in the reduced gravity environment. The size and distribution of rocks in a given area often indicate the history of impact events and volcanic activity that shaped the local geology. Lava tubes formed by ancient volcanic activity create some of the moon's most promising natural shelters. These underground cavities formed when molten lava flowed beneath a solidified crust, leaving behind hollow tubes that can extend for kilometers beneath the surface. The entrances to lava tubes appear as circular or elliptical openings in otherwise flat terrain, often surrounded by collapsed ceiling material that creates distinctive mound formations. Identifying lava tube entrances requires careful observation of surface features that seem inconsistent with impact crater formation. Unlike the raised rims typical of impact craters, lava tube openings often appear as depressions with gently sloping sides and irregular shapes. The surrounding terrain may show evidence of ancient lava flows in the form of smooth, rope-like rock formations, or areas where the surface appears to have flowed around obstacles. The absence of weather on the moon means that surface features remain unchanged for millions of years, creating a landscape where geological processes operate on vastly different timescales than those familiar from Earth. This stability means that any unusual formation or surface disturbance represents a significant event worth investigating for survival potential. Avalanche scars, where loose material has slumped down crater walls, indicate areas of structural instability that should be avoided but may also reveal subsurface materials not visible elsewhere. Navigation across the lunar surface requires abandoning terrestrial assumptions about travel and orientation. The horizon appears much closer than on Earth due to the moon's smaller radius, creating a sense of walking across a small spherical world rather than a vast planetary surface. This foreshortened perspective can lead to serious misjudgments about distance and scale, causing you to underestimate travel times and energy requirements for reaching visible landmarks. Dust devil formations, while rare, do occur on the moon due to electrostatic effects rather than atmospheric circulation. These phenomena appear as swirling columns of charged particles that rise from the surface during certain lighting conditions, particularly near the terminator line, where day transitions to night. While not dangerous in the meteorological sense, these electrical discharges can interfere with electronic equipment and create hazardous static buildups on metal surfaces. The lunar surface contains subtle color variations that become apparent under proper lighting conditions, indicating different mineral compositions that might affect survival planning. Areas rich in iron oxide appear slightly reddish, while regions with high aluminum content show brighter, whiter tones. These compositional differences influence thermal properties, with darker materials absorbing more heat during lunar day and radiating it more efficiently during nighttime cooling. Slope stability presents unique challenges in the reduced gravity environment, where loose material behaves differently than terrestrial expectations would suggest. Steep crater walls that appear stable may actually be held in place only by the moon's weak gravitational pull, making them prone to sudden avalanches when disturbed by seismic activity or human movement. Understanding angle of repose for lunar materials helps identify potentially unstable slopes that should be avoided during shelter selection. The boundaries between different geological units often provide the most valuable survival resources, as these transition zones frequently contain exposed materials from various formation processes. Contact zones between ancient lava flows and impact crater formations may reveal mineral deposits or structural features not found in uniform terrain. These boundaries appear as subtle changes in surface texture, color, or rock distribution that require careful observation to identify. Micrometeorite impact patterns create ongoing changes to the lunar surface that affect navigation and safety planning. Fresh impact sites appear as bright spots or rays extending outward from small craters, indicating recent disturbance of the surface material. While individual micrometeorite impacts pose minimal direct threat, the cumulative effect over time gradually alters the landscape and exposes fresh materials that might be useful for survival purposes. As you stand in this ancient landscape, every shadow cast by every rock tells a story about solar angles, surface composition, and potential shelter opportunities. The dust beneath your feet contains the history of cosmic bombardment, while the craters around you offer glimpses into the moon's violent past and your possible future refuge. Learning to read these silent messages transforms the alien landscape into a library of survival information, written in the universal language of geology and illuminated by the unforgiving light of an unfiltered sun. The lunar terrain demands patience and careful observation, rewarding those who take time to understand its subtle communications with vital information about shelter, resources, and safe passage. In this world without weather or erosion, Every feature has meaning, and every shadow holds secrets that might determine whether you survive to see another Earth rise over the lunar horizon. Radiation streams through space with the silent persistence of an unseen predator, carrying energy levels that can rewrite the fundamental chemistry of living cells. On Earth, our planet's magnetic field and thick atmosphere shield us from this cosmic bombardment, but the moon offers no such protection against the invisible forces that permeate the universe beyond our home world. Understanding radiation becomes essential for survival because the effects accumulate gradually, often without immediate symptoms that would warn you of dangerous exposure levels. Unlike the obvious threats of oxygen depletion or temperature extremes, radiation damage occurs at the cellular level through processes that may not manifest for hours, days, or even years after initial exposure. This delayed response makes radiation simultaneously one of the most dangerous and most underestimated hazards of lunar survival. Solar radiation arrives in two distinct forms that require different protection strategies. Electromagnetic radiation travels at light speed and includes ultraviolet rays, X-rays, and gamma radiation that can penetrate deeply into human tissue. Solar particle radiation consists of high-energy protons and heavy ions ejected from the sun's surface during solar flares and coronal mass ejections, creating streams of charged particles that can cause immediate cellular damage upon contact with living tissue. The intensity of solar radiation varies dramatically with the sun's 11-year activity cycle and can increase by orders of magnitude during solar storm events. During periods of high solar activity, particle radiation levels can exceed safe exposure limits within hours, making immediate shelter essential for survival. These particle storms appear as invisible waves of destruction that sweep across the lunar surface at speeds approaching 1,000 kilometers per second. Galactic cosmic rays present a constant background threat that originates from sources throughout our galaxy and beyond. These high-energy particles possess enough energy to penetrate several meters of solid rock, making them difficult to shield against using available materials. Unlike solar radiation, cosmic ray intensity remains relatively constant, but represents a cumulative threat that increases total radiation exposure over extended periods. The moon's lack of atmosphere means that radiation reaches the surface at full intensity without the filtering effects that protect Earth's inhabitants. Ultraviolet radiation alone exceeds safe exposure limits within minutes of direct contact with unprotected skin or eyes. This intense electromagnetic bombardment can cause severe burns, cataracts, and cellular damage that begins immediately upon exposure, but may not produce visible symptoms until hours later. Natural radiation shielding becomes possible using lunar geography and available materials in ways that work with, rather than against, the laws of physics. Dense materials, such as rock and metal, provide the most effective protection per unit thickness, while the lunar regolith itself contains enough mass to significantly reduce radiation penetration when piled to sufficient depth. Every centimeter of rock or regolith between you and the radiation source reduces exposure levels through absorption and scattering processes. Crater walls offer some of the best natural radiation protection available on the lunar surface, particularly when combined with their thermal and mechanical shelter benefits. The raised rim of a crater creates a physical barrier that blocks radiation arriving from specific directions, while the depression itself provides additional shielding from overhead sources. Positioning yourself against the wall of a crater during high radiation periods can reduce exposure levels by 50% or more compared to open surface conditions. Lava tubes represent the ultimate natural radiation shelter, providing protection equivalent to several meters of solid rock while maintaining accessible interior spaces. These underground formations shield occupants from radiation arriving from all directions, creating safe zones where extended stays become possible without exceeding dangerous exposure limits. The challenge lies in locating and accessing these natural shelters while managing other survival priorities. Improvised radiation shielding using spacecraft debris and available equipment requires understanding the relationship between material density and shielding effectiveness. Metallic components from damaged spacecraft provide excellent protection per unit weight, while plastic and fabric materials offer minimal shielding benefits despite their availability. Water, if available, serves as an excellent radiation shield while also fulfilling other survival needs. Creating effective radiation barriers involves layering different materials to address various types of radiation simultaneously. Dense metals provide primary protection against high-energy particles, while lighter materials help moderate secondary radiation produced when primary particles interact with heavy shielding materials. This layered approach maximizes protection efficiency while conserving limited material resources. Recognition of radiation exposure symptoms becomes critical for managing your health during extended lunar stays. Acute radiation syndrome develops within hours of severe exposure and includes nausea, fatigue, skin reddening, and digestive problems that indicate cellular damage throughout the body. Lower-level chronic exposure produces more subtle symptoms such as fatigue, immune system suppression, and increased susceptibility to infections that may not become apparent for days or weeks. The absence of medical facilities means that radiation exposure treatment relies entirely on prevention rather than intervention after symptoms appear. Once cellular damage occurs, the human body's natural repair mechanisms must address the problem without pharmaceutical assistance or advanced medical procedures. This reality makes conservative exposure management the only viable strategy for maintaining long-term health during lunar survival situations. Timing activities to minimize radiation exposure requires understanding the patterns of solar activity and cosmic ray variations. Solar particle events often provide several hours of advance warning through increased electromagnetic emissions that precede the arrival of dangerous particle streams. Monitoring these early warning signals, when possible, allows you to seek shelter before radiation levels become life-threatening. The lunar day-night cycle affects radiation exposure patterns in ways that differ significantly from terrestrial expectations. During lunar day, direct solar radiation creates the primary threat, while cosmic ray exposure remains constant throughout the day-night cycle. Permanently shadowed regions provide excellent protection from solar radiation, but offer no additional shielding against cosmic rays originating from deep space. Electronic equipment provides indirect radiation monitoring through observed malfunctions and performance degradation caused by particle bombardment of sensitive components. Digital displays may show static or random patterns. Communication devices might experience increased noise levels, and computer systems could exhibit processing errors that indicate elevated radiation environments. These equipment responses serve as early warning indicators when dedicated radiation monitoring instruments are unavailable. Creating radiation exposure logs becomes essential for tracking cumulative dose levels over extended periods. Without accurate dosimetry equipment, exposure estimates must rely on time-based calculations using known radiation levels for different lunar environments and shielding configurations. Maintaining detailed records of shelter usage, activity levels, and equipment performance helps estimate total exposure and guide future safety decisions. The psychological aspects of radiation protection require balancing realistic threat assessment against paralyzing fear of invisible dangers. Radiation represents a statistical risk rather than an immediate certain threat, meaning that brief exposures during necessary activities pose manageable risks, while prolonged unshielded exposure becomes increasingly dangerous. Understanding this risk gradient helps maintain rational decision-making under stress. Emergency radiation protocols focus on minimizing exposure time, maximizing distance from sources, and optimizing available shielding materials. The inverse square law means that doubling your distance from a radiation source reduces exposure levels by 3/4, making even small increases in separation distance beneficial for safety. When seeking shelter is impossible, maintaining maximum possible distance from obvious sources provides measurable protection benefits. Long-term radiation management requires establishing sustainable routines that balance protection needs against other survival priorities. Complete isolation in maximum protection shelters quickly becomes impractical due to resource limitations and the need to perform essential survival activities. Developing schedules that allocate high-risk activities to periods of lower radiation intensity helps minimize cumulative exposure while maintaining necessary operations. The lunar environment transforms radiation from an abstract concept studied in physics textbooks into a tangible survival challenge that demands constant awareness and respect. This invisible enemy requires the same careful planning and resource management as more obvious threats, but with the added complexity of delayed consequences that make risk assessment difficult. Success depends on treating radiation protection as an integral component of every survival decision, rather than an optional safety consideration that can be addressed when convenient. In the silence of the lunar landscape, where no atmospheric molecules exist to absorb or scatter the deadly streams of particles and energy flowing through space, radiation becomes both omnipresent and manageable through informed planning and judicious use of natural and artificial barriers. The invisible enemy yields to knowledge, preparation, and the fundamental principles of physics that govern the interaction between matter and energy in the cosmos beyond Earth's protective embrace. During the final moments before lunar sunset, temperatures across the moon's surface hover near the boiling point of water at 127 degrees Celsius, hot enough to melt lead and pose immediate threats to any exposed equipment or human tissue. Yet within 14 Earth days, that same landscape will experience temperatures plunging to -173 degrees Celsius, colder than the surface of Pluto and sufficient to freeze carbon dioxide into solid chunks. This temperature swing of 300 degrees Celsius represents one of the most extreme thermal environments in our solar system, creating survival challenges that push human physiology and technology far beyond their design limits. The lunar day lasts 29.5 Earth days, meaning that sunrise and sunset occur with agonizing slowness, providing both extended warning periods and prolonged exposure to temperature extremes that would be brief events on our home planet. The absence of atmospheric thermal buffering means that temperature changes occur through direct radiation exchange between surfaces and the cold vacuum of space. Without air molecules to store and distribute thermal energy, the lunar surface responds immediately to changes in solar illumination, heating rapidly when exposed to sunlight and cooling equally quickly once shadows fall. This direct relationship between illumination and temperature creates microenvironments where dramatic temperature variations can exist within distances measured in meters rather than kilometers. Understanding thermal physics becomes essential for survival because your body represents a complex heat engine that must maintain core temperature within narrow limits to preserve essential biological functions. Human survival requires maintaining internal body temperature between 36 and 38 degrees Celsius, with deviations of more than a few degrees triggering physiological responses that can quickly become life-threatening in extreme environments. Your pressure suit provides the primary thermal barrier between your body and the lunar environment, but this protection operates within finite limits determined by battery power, coolant supplies, and mechanical integrity. During lunar day conditions, the suit's cooling system works continuously to prevent overheating, while nighttime operations depend on heating elements that consume precious electrical power. Understanding these systems helps optimize thermal management strategies that extend survival duration. Heat transfer occurs through three fundamental mechanisms that each require different management approaches in the lunar environment. Conduction transfers thermal energy through direct contact between materials, meaning that touching extremely hot or cold surfaces can cause immediate tissue damage despite protective equipment. Radiation exchange occurs between all surfaces regardless of physical contact, causing your body to both absorb heat from warm objects and lose heat to cooler surroundings. Convection, the thermal transfer mechanism most familiar from terrestrial experience, cannot occur in the lunar vacuum because it requires fluid movement to carry thermal energy between locations. This absence of convective cooling or heating means that thermal management depends entirely on conduction and radiation processes that operate according to different rules than atmospheric environments. Solar heating during lunar day creates thermal loads that exceed the cooling capacity of most portable life support systems within hours of continuous exposure. Direct sunlight delivers approximately 1,400 watts of thermal energy per square meter of surface area, enough to power several household appliances or quickly overwhelm personal thermal management systems. Seeking shade becomes essential for preventing heat exhaustion and equipment failure during daylight operations. The lunar regolith beneath your feet acts as both thermal reservoir and insulation layer, storing heat during day periods and slowly releasing it throughout the long lunar night. This thermal mass effect means that surface temperatures lag behind solar illumination patterns, with peak heating occurring several hours after local noon and minimum temperatures reach just before sunrise. Understanding these thermal delays helps predict safe activity windows for surface operations. Rock formations and crater walls create complex thermal environments where temperature variations depend on solar illumination angles, surface orientation, and thermal mass distribution. South-facing slopes receive maximum solar heating and maintain higher temperatures longer, while north-facing surfaces remain cooler throughout the lunar day. These orientation effects create temperature differences of 50 degrees Celsius or more within small geographic areas. Permanently shadowed regions maintain temperatures below minus 200 degrees Celsius throughout the lunar day-night cycle, creating environments so cold that common materials become brittle and mechanical systems cease functioning entirely. While these areas may contain valuable water ice deposits, the extreme cold presents immediate threats to equipment integrity and human survival that require careful preparation and specialized techniques. Thermal regulation strategies must balance heat generation against heat loss while managing finite energy resources and equipment limitations. Physical activity generates metabolic heat that helps maintain body temperature during cold periods, but increases cooling requirements during hot conditions. Finding optimal activity levels requires understanding your body's thermal response patterns and adjusting behavior to match environmental conditions. Improvised thermal management using available materials requires understanding the thermal properties of different substances and their effectiveness as insulation or thermal mass. Metallic spacecraft components conduct heat efficiently, making them useful for transferring thermal energy, but dangerous for direct contact during temperature extremes. Fabric materials provide insulation benefits, but may degrade rapidly under extreme temperature cycling. Creating thermal barriers using lunar regolith takes advantage of the insulating properties of loose granular materials while utilizing abundant local resources. Piling regolith against shelter walls or around equipment creates insulation layers that moderate temperature swings, though the effectiveness depends on thickness and proper placement to minimize thermal bridges that conduct heat around the barriers. The lunar vacuum provides excellent insulation properties that can be utilized for thermal management when properly contained. Creating dead air spaces within shelters or around equipment prevents convective heat loss while utilizing the vacuum's natural resistance to thermal conduction. However, achieving effective vacuum insulation requires careful sealing to prevent gas infiltration that would reduce insulating effectiveness. Recognizing hypothermia and hyperthermia symptoms becomes critical for medical management when sophisticated monitoring equipment is unavailable. Hypothermia develops gradually as core body temperature drops, beginning with shivering and progressing through confusion, loss of coordination, and eventual loss of consciousness. Hyperthermia produces rapid heartbeat, dizziness, and profuse sweating that can quickly progress to heat stroke and organ failure. Emergency thermal treatment protocols focus on gradual temperature correction to avoid thermal shock that can cause additional physiological damage. Rapid rewarming of frozen tissue can cause more harm than gradual temperature recovery, while too rapid cooling during heat emergencies can trigger cardiovascular complications. Understanding proper thermal first aid techniques prevents well-intentioned treatments from creating additional medical emergencies. Thermal cycling effects on equipment and materials create ongoing maintenance challenges that affect long-term survival prospects. Repeated expansion and contraction caused by temperature variations can cause mechanical failures, seal degradation, and material fatigue that compromise critical systems. Monitoring equipment performance and implementing preventive maintenance helps identify thermal damage before it causes complete system failures. Energy conservation strategies must account for increased power consumption during temperature extremes while managing limited battery supplies and charging capabilities. Heating and cooling systems represent major power drains that can quickly exhaust available energy reserves if not carefully managed. Developing power budgets that prioritize essential thermal management while minimizing non-critical energy consumption extends survival duration during extended temperature extremes. The psychological challenges of extreme temperature environments include the constant awareness of thermal threats and the stress of managing complex thermal protection systems. The knowledge that equipment failure could result in rapid heating or cooling beyond survival limits creates ongoing anxiety that affects decision-making and overall mental health. Developing confidence in thermal management procedures and backup systems helps maintain psychological stability during temperature crises. Long-term thermal planning requires establishing sustainable patterns that account for the lunar day-night cycle while managing resource consumption and equipment maintenance. The 14-day periods of continuous heating or cooling exceed the endurance limits of most portable systems, making resource conservation and thermal efficiency essential for extended survival. Creating schedules that minimize thermal stress while maintaining necessary activities becomes a complex optimization problem. As shadows lengthen across the lunar landscape and surface temperatures begin their relentless slide toward the deadly cold of lunar night, thermal management transforms from a technical consideration into the fundamental challenge that determines survival or death. The sun that provided life-giving warmth during the day becomes a distant, insufficient source of thermal energy, while the lunar surface radiates its stored heat into the infinite cold of space. Understanding and managing these thermal extremes requires treating temperature as both ally and enemy, harnessing thermal energy when available while protecting against thermal extremes that can kill within minutes of unprotected exposure. Consider the profound absurdity that in a universe where water exists in vast quantities throughout distant galaxies, on this particular world just 384,000 kilometers from Earth, every molecule of hydrogen and oxygen represents precious currency that might determine whether you survive another day. The moon contains water, locked away in permanently shadowed craters and chemically bound within rock formations, but extracting and purifying these resources requires techniques that push improvisation beyond conventional limits. Your daily water requirements increase significantly under the stress of lunar survival conditions. Despite the absence of atmospheric humidity that might otherwise accelerate fluid loss through perspiration, the human body requires approximately 3 liters of water per day under normal Earth conditions, but emergency survival scenarios increase this requirement to 4 or 5 liters daily due to elevated stress responses, altered circulation patterns in reduced gravity, and increased respiratory water loss in the dry environment of recycled air systems. Water serves multiple critical functions beyond basic hydration in the lunar survival context. It provides thermal mass for temperature regulation, serves as an effective radiation shield when positioned between you and radiation sources, and can be electrolyzed to produce both oxygen for breathing and hydrogen for potential fuel applications. This multifunctional value means that every drop recovered represents multiple survival benefits rather than simply addressing thirst. The lunar poles contain the most accessible water ice deposits, concentrated in permanently shadowed regions where temperatures remain below -200 degrees Celsius throughout the lunar day-night cycle. These deposits formed over billions of years as water molecules from comet impacts and solar wind interactions became trapped in areas where sunlight never reaches. However, accessing these resources requires traveling to specific geographic locations and working in extremely cold conditions that present their own survival challenges. Improvised water extraction from lunar ice requires understanding the physics of sublimation and condensation in vacuum environments. Ice sublimes directly from solid to vapor phase in lunar conditions, bypassing the liquid state entirely due to low atmospheric pressure. Capturing and condensing these water vapors demands creating controlled environments where pressure and temperature conditions allow vapor to liquid phase transitions. Solar concentrators, constructed from reflective spacecraft materials, can provide the thermal energy needed to sublimate ice deposits and drive water extraction processes. Polished metal surfaces, reflective thermal blankets, or even curved sections of spacecraft hull can be arranged to focus sunlight onto ice-bearing regolith samples, generating enough heat to release water vapor that can then be captured and condensed in improvised collection systems. Condensation traps require creating cold surfaces where water vapor can return to liquid or solid phase for collection. In the lunar environment, any surface shielded from direct sunlight quickly becomes cold enough to condense water vapor, but collection systems must also provide containment to prevent the collected water from subliming back into vapor. Simple collection methods include plastic bags, metal containers, or improvised funneling systems that direct condensed water into storage vessels. Humidity recovery from breathing and perspiration represents another water source that becomes critical during extended survival periods. The human body releases approximately 1 liter of water daily through respiration and skin moisture, water that would normally be lost to the environment but can be captured and recycled using improvised systems. Breathing into enclosed containers or using fabric materials to capture exhaled moisture provides recoverable water that requires minimal processing. Water purification becomes essential because lunar water sources may contain dissolved minerals, dust contamination, or chemical compounds that pose health risks if consumed directly. Ice extracted from lunar deposits may contain perchlorate compounds or other toxic substances that require removal before the water becomes safe for drinking. Simple filtration through fabric materials removes particulate contamination, while boiling or UV exposure can eliminate potential biological contaminants. Emergency water rationing protocols balance immediate hydration needs against long-term resource conservation while maintaining cognitive function and physical performance. Severe dehydration develops within hours in emergency conditions, but overconsumption of limited water supplies creates equally dangerous resource depletion scenarios. Optimal rationing strategies provide sufficient water to maintain essential bodily functions, while extending supply duration to maximize rescue opportunities. Dehydration symptoms in the lunar environment may differ from terrestrial experiences due to altered gravitational effects on circulation and the stress responses associated with survival scenarios. Early dehydration signs include decreased urine production, increased thirst, and mild headaches that can be confused with other stress-related symptoms. Advanced dehydration produces rapid heartbeat, dizziness, and confusion that severely impair decision-making capabilities when clear thinking becomes most critical. Water recycling systems can be improvised using available materials to extend supply duration through multiple use cycles. Simple recycling involves collecting all liquid waste and processing it through filtration and purification steps to remove contaminants and restore potability. While psychologically challenging, urine recycling represents a significant water recovery opportunity that established space programs utilize routinely in closed-loop life support systems. Underground water sources may exist in areas where ancient volcanic activity created subsurface ice deposits or where impact events exposed water-bearing rock formations. These sources require excavation techniques using available tools and may be located through careful observation of geological features that suggest subsurface water presence. Excavation in reduced gravity allows moving larger amounts of material than would be practical under Earth conditions. Chemical water production represents an advanced technique that creates water through chemical reactions using available materials and energy sources. Hydrogen and oxygen can be produced through electrolysis of any existing water supplies, then recombined through controlled combustion to generate additional water while also producing useful energy. However, these processes require sophisticated equipment and energy inputs that may not be available in emergency survival situations. Conservation techniques focus on minimizing water loss through careful management of consumption patterns and elimination of unnecessary waste. Drinking small amounts frequently proves more efficient than consuming large quantities at irregular intervals, as the body can absorb and utilize smaller doses more effectively. Avoiding activities that increase perspiration or respiratory water loss helps preserve supplies during critical shortage periods. Storage and preservation of recovered water requires protecting supplies from freezing, evaporation, and contamination while maintaining accessibility for consumption. Water freezes rapidly in lunar conditions, potentially damaging storage containers and making access difficult when supplies are needed. Insulation techniques using available materials help moderate temperature extremes, while sealed containers prevent loss through sublimation. The psychological aspects of water scarcity create stress responses that can actually increase water requirements while impairing rational resource management decisions. Anxiety about water supplies can trigger physiological responses that elevate fluid needs, while the mental stress of rationing decisions affects cognitive function needed for effective survival planning. Understanding these psychological factors helps maintain rational water management practices under pressure. Long-term water sustainability requires establishing extraction and purification routines that can be maintained throughout extended survival periods without depleting available energy and material resources. Balancing water production efforts against other survival priorities becomes an optimization challenge, where success depends on finding efficient techniques that provide adequate supplies without consuming excessive time and resources needed for other critical activities. Advanced recovery techniques may become possible as equipment failures provide access to internal components that can be repurposed for water processing applications. Cooling systems contain refrigerants and heat exchange components that can be modified for condensation applications, while electronic components may provide materials useful for constructing filtration or purification systems. Creative repurposing of available technology expands water recovery options beyond conventional approaches. Water management transforms from a simple matter of turning on a faucet into a complex engineering challenge that requires understanding phase transitions, chemical processes, and biological requirements while working within severe resource constraints. Every collection technique becomes vital, and every drop recovered represents another increment of survival time in an environment where abundance and scarcity exist simultaneously. Abundant water locked in ancient ice deposits, scarce water available for immediate consumption without sophisticated extraction and processing techniques that push human ingenuity to its limits. In the stark lunar landscape, where water exists primarily as ancient ice deposits and chemical compounds, successful hydration strategies require treating each recovered drop as both immediate life support and investment in continued survival, balancing consumption against conservation in calculations that measure time in drops rather than gallons. Between this breath and your next lies a calculation that your body performs automatically millions of times throughout a lifetime. But on the lunar surface, each respiratory cycle becomes a conscious transaction with finite resources measured in hours rather than unlimited atmospheric abundance. Your portable life support system contains precisely calculated quantities of oxygen, and every inhalation draws from reserves that diminish with mathematical certainty toward a moment when the final breath must be drawn from an empty tank. Human respiratory requirements vary dramatically based on physical activity, stress levels, and environmental conditions that affect metabolic demands on oxygen-dependent cellular processes. At rest, the average adult consumes approximately 0.25 liters of oxygen per minute, but physical exertion can increase this rate to 2 liters per minute or higher during periods of intense activity. Understanding these consumption patterns becomes essential for calculating survival duration and managing activities to extend oxygen supply longevity. The reduced gravity environment affects respiratory physiology in ways that both conserve and consume oxygen reserves through complex interactions between cardiovascular function and metabolic requirements. Lower gravitational stress reduces the cardiac workload needed to pump blood throughout the body, potentially decreasing overall oxygen consumption during light activities. However, the unfamiliar movement patterns required in 1/6 gravity can increase energy expenditure as muscles work to maintain balance and coordination in the altered physical environment. Stress responses triggered by survival scenarios significantly increase oxygen consumption through elevated heart rate, deeper breathing patterns, and metabolic changes associated with adrenaline release. These physiological responses can increase oxygen usage by 50% or more above normal resting levels, making stress management an essential component of oxygen conservation strategies. Controlled breathing techniques and conscious relaxation practices help minimize stress-induced consumption increases. Carbon dioxide removal becomes equally critical as oxygen supply management because accumulating carbon dioxide produces toxic effects that can incapacitate or kill even when adequate oxygen remains available. The human body produces approximately 0.8 liters of carbon dioxide for every liter of oxygen consumed, creating waste gas that must be removed from breathing air to prevent carbon dioxide poisoning. Life support systems include chemical scrubbers that absorb carbon dioxide, but these systems have finite capacity that must be managed alongside oxygen supplies. Emergency breathing techniques developed for diving and high-altitude applications can extend oxygen supplies by optimizing respiratory efficiency and reducing wasteful breathing patterns. Box breathing, where inhalation, breath holding, exhalation, and pause phases each last 4 seconds, slows respiratory rate while maintaining adequate oxygen uptake. This controlled breathing pattern can reduce oxygen consumption by 15 to 20%, while also helping manage stress responses that otherwise increase metabolic demands. Physical activity management requires balancing necessary survival tasks against oxygen consumption rates that vary dramatically with exertion levels. Walking on the lunar surface consumes approximately twice the oxygen of resting activities, while tasks requiring physical strength or rapid movement can increase consumption rates by 5 to 10 times above baseline levels. Planning activities to minimize high consumption periods helps extend survival duration while maintaining essential operational capabilities. Altitude sickness medications and techniques may prove useful for managing reduced atmospheric pressure effects, even though the lunar environment represents vacuum exposure rather than high-altitude conditions. The physiological responses to reduced atmospheric pressure share similarities with altitude-related symptoms, including headaches, dizziness, and cognitive impairment that affect decision-making capabilities. Understanding these parallels helps identify management strategies that address symptoms while conserving oxygen resources. Emergency oxygen generation represents an advanced survival technique that creates breathable gas through chemical reactions or electrolysis processes using available materials and energy supplies. Hydrogen peroxide decomposition releases oxygen gas that can supplement portable supplies, though this process requires catalysts and safety precautions to prevent explosive reactions. Electrolysis of water produces oxygen and hydrogen gases, but requires significant electrical power that may not be available in emergency situations. Oxygen concentration monitoring becomes critical for maintaining safe breathing environments while avoiding wasteful overventilation that depletes supplies unnecessarily. The human body can function on oxygen concentrations as low as 16% compared to the 21% found in Earth's atmosphere. Monitoring and maintaining optimal oxygen levels prevents both hypoxia from insufficient oxygen and waste from excessive gas usage. Improvised carbon dioxide scrubbing systems can extend the usable lifetime of limited oxygen supplies by removing waste gases that would otherwise create toxic breathing environments. Sodium hydroxide, lithium hydroxide, and other alkaline materials react with carbon dioxide to form solid compounds that can be removed from breathing air. These materials may be available from spacecraft life support systems or improvised from other chemical sources. Respiratory health maintenance requires preventing lung damage from dust inhalation while managing the dry air conditions, typical of recycled atmosphere systems. Lunar dust contains razor-sharp particles that can cause permanent lung damage if inhaled, making respiratory protection essential during any activities that might disturb surface materials. Maintaining adequate humidity in breathing air helps prevent respiratory tract irritation that can increase oxygen demands. Shared breathing systems allow multiple survivors to benefit from collective oxygen management while distributing consumption loads across available supplies. These systems require careful planning to prevent contamination and ensure equitable distribution but can significantly extend survival time for groups compared to individual resource management. However, shared systems also create risks if one person's higher consumption patterns deplete collective supplies. Sleep and rest cycle optimization affects oxygen consumption patterns through metabolic rate variations that occur during different sleep phases and conscious rest periods. Sleep typically reduces oxygen consumption by 20 to 30% below waking resting levels, making adequate rest an essential component of resource conservation. However, stress and uncomfortable conditions may prevent restful sleep that would otherwise provide conservation benefits. Emergency protocols for oxygen system failures require immediate response procedures that maximize survival chances when primary life support systems malfunction. Breath-holding techniques can provide several minutes of survival time while attempting repairs or accessing backup systems. Understanding the progression of hypoxia symptoms helps identify when emergency measures become necessary and guides decision-making during critical equipment failures. Psychological management of oxygen anxiety requires balancing realistic resource monitoring against paralyzing fear that increases consumption through stress responses. Constant awareness of diminishing oxygen supplies can create feedback loops where anxiety about supplies increases consumption rates, accelerating resource depletion. Developing confidence in consumption calculations and emergency procedures helps maintain rational resource management under pressure. Activity scheduling based on oxygen efficiency principles maximizes survival duration by matching high consumption activities to periods when resource expenditure provides maximum benefit for essential survival tasks. Grouping physically demanding activities reduces the total time spent at elevated consumption rates, while scheduling rest periods provides recovery opportunities that restore baseline consumption patterns. Long-term oxygen planning requires calculating consumption patterns over extended periods while accounting for changing environmental conditions and resource availability. The lunar day-night cycle affects thermal management requirements that influence overall metabolic demands, while potential rescue timelines determine minimum survival duration requirements. These calculations help establish sustainable activity levels that maintain essential functions while preserving resources for extended periods. Advanced conservation techniques may include deliberately reducing metabolic rates through controlled hypothermia or meditation practices that slow respiratory and cardiac function below normal levels. These extreme measures carry significant health risks, but might provide additional survival time during critical shortages. Understanding the risks and procedures for metabolic suppression techniques provides options during desperate circumstances. In the silence of the lunar vacuum, where no wind carries the scent of fresh air and no atmospheric pressure gradient creates the breathing sensation familiar from Earth, each breath becomes a deliberate act of resource management that connects the automatic processes of human physiology with the finite mathematics of survival engineering. The breathing calculator runs continuously, measuring inhalations against remaining supplies while balancing immediate oxygen needs against long-term survival requirements in calculations that transform the simple act of breathing into complex life support mathematics. How might you transform the ancient geological formations beneath your feet into sources of power that could determine the difference between survival and slow death in the lunar wilderness? The moon contains abundant energy resources locked within rock formations, mineral deposits, and the relentless bombardment of solar radiation. But accessing these resources requires understanding fundamental principles of chemistry and physics while working with improvised equipment under extreme conditions. Solar energy represents the most immediate and abundant power source available on the lunar surface, delivering approximately 1,400 watts per square meter of direct sunlight without atmospheric filtering or weather interruptions. This energy density exceeds terrestrial solar conditions by roughly 40% due to the absence of atmospheric absorption and scattering effects. However, the lunar day-night cycle creates 14-day periods of continuous darkness that require energy storage or alternative power generation methods. Photovoltaic panels, salvaged from spacecraft systems, provide direct conversion of solar energy into electrical power, but their efficiency depends on proper orientation, temperature management, and freedom from dust contamination that can significantly reduce power output. Lunar dust adheres electrostatically to solar panel surfaces, creating opaque layers that block sunlight and reduce electrical generation. Regular cleaning using improvised techniques becomes essential for maintaining power generation capacity. Concentrated solar power systems can be constructed using reflective materials to focus sunlight onto thermal absorption surfaces that convert heat energy into useful work or electrical generation. Parabolic reflectors, fashioned from curved spacecraft hull sections or polished metal components, can concentrate solar energy to temperatures exceeding 1,000 degrees Celsius, sufficient for thermochemical processes or thermal electric power generation using available materials. Thermal electric generation utilizes temperature differences to produce electrical power through semiconductor effects that convert thermal gradients directly into electrical current. The extreme temperature variations between sunlit and shadowed lunar surfaces create ideal conditions for thermal electric power generation using devices constructed from available electronic components. These systems require minimal moving parts and can operate continuously as long as temperature differentials exist. Battery management becomes critical for storing electrical energy during solar charging periods for use during darkness or when solar panels cannot operate effectively. Lithium-ion batteries from spacecraft systems provide high energy density but require careful thermal management to prevent overheating during charging or freezing during discharge cycles. Understanding battery chemistry helps optimize charging patterns and prevent damage from overcharging or deep discharge conditions. Chemical energy stored in spacecraft fuel supplies represents high-density power sources that can be converted into thermal or electrical energy through controlled combustion or fuel cell reactions. Hydrazine, hydrogen peroxide, and other rocket fuels contain substantial energy that can power heating systems or electrical generators when used with proper safety precautions. However, these materials require careful handling to prevent accidental explosions or toxic exposure. Radioisotope thermoelectric generators may be available from certain spacecraft systems, providing continuous power generation through radioactive decay processes that operate independently of solar conditions. These systems generate modest electrical power outputs, but function reliably for years without maintenance or fuel supplies. Locating and accessing these power sources requires understanding spacecraft design and radiation safety protocols. Kinetic energy conversion systems can harvest mechanical energy from available sources such as thermal expansion, structural vibrations, or manual operation to generate electrical power for essential systems. Hand-cranked generators, spring-powered mechanisms, or thermal expansion engines can produce power through human effort or environmental energy sources. These systems provide backup power options when other generation methods fail. Energy conservation strategies focus on minimizing power consumption through efficient equipment operation and eliminating non-essential electrical loads that drain limited battery supplies. LED lighting consumes significantly less power than incandescent alternatives, while electronic devices often include power-saving modes that reduce consumption during standby periods. Prioritizing essential functions helps extend available power duration. Power distribution systems must be improvised using available wiring and electronic components to deliver electrical energy from generation sources to critical loads, such as life support systems, communication equipment, and thermal management devices. Understanding basic electrical principles helps prevent short circuits, overloads, and other failures that could damage equipment or create safety hazards. Thermal management of power systems requires preventing overheating of electrical components while maintaining operating temperatures that ensure reliable function. Electronic components generate waste heat during operation that must be dissipated to prevent failures, while extreme cold can cause semiconductors and batteries to malfunction. Creating thermal regulation systems helps maintain optimal operating conditions for power equipment. Fuel synthesis represents an advanced technique that creates chemical energy sources through processing of lunar materials and available resources. Hydrogen and oxygen can be produced through water electrolysis and stored as chemical fuel for combustion or fuel cell applications. These processes require significant energy investment, but can create storable fuel supplies that provide power during periods when direct generation is impossible. Energy storage beyond batteries might include mechanical systems such as compressed air, wound springs, or elevated masses that store potential energy for later conversion to useful work. These systems require construction materials and mechanical expertise, but can provide energy storage alternatives when battery capacity becomes insufficient for survival requirements. Power system monitoring involves tracking energy generation, consumption, and storage levels to optimize resource utilization while preventing critical system failures due to power shortages. Simple voltage measurements and consumption timing help identify energy usage patterns and guide decisions about when to operate high-consumption devices. Understanding power system status prevents unexpected equipment shutdowns during critical operations. The emergency power protocols establish procedures for managing power crises when generation capacity drops below consumption requirements or when critical power systems fail. Load shedding techniques identify which systems can be temporarily shut down to preserve power for essential life support functions. These protocols help maintain critical operations during power emergencies while conserving energy for essential functions. Waste heat recovery systems capture thermal energy from electronic equipment, human body heat, and other sources to provide useful heating or power generation capabilities. Heat exchangers, constructed from available materials, can transfer waste thermal energy to useful applications such as water heating or thermal electric generation. This approach improves overall energy efficiency by utilizing otherwise wasted energy sources. Power tool construction involves creating mechanical devices that amplify human effort or provide specialized capabilities using available materials and energy sources. Hand tools powered by mechanical advantage systems, pneumatic devices using compressed gases, or electrically powered equipment help accomplish tasks that would otherwise be impossible with human strength alone. These tools extend survival capabilities while managing energy consumption. Grid storage techniques allow multiple power sources to be combined and managed collectively to provide more reliable and higher capacity electrical systems. Connecting solar panels, batteries, and other power sources through improvised switching systems creates redundant power supplies that continue operating even if individual components fail. This approach improves overall system reliability and power availability. Long-term sustainability of power systems requires maintaining generation capacity, storage systems, and distribution networks throughout extended survival periods while managing component degradation and resource depletion. Regular maintenance, cleaning, and repair activities help preserve power system function, while resource recycling and conservation extend the operational lifetime of critical power equipment. Advanced generation techniques might include constructing wind turbines, using available materials to harvest energy from gas releases or mechanical rotation systems, though these approaches require significant construction effort and may have limited applicability in the lunar vacuum environment. Understanding diverse power generation principles provides options for creative solutions when conventional approaches prove insufficient. In the harsh lunar environment, where power represents the fundamental currency that determines whether life support systems continue operating or fail catastrophically, transforming rocks and debris into energy sources becomes an essential survival skill that connects geological resources with electrical engineering in pursuit of the power needed to maintain human life in an environment that offers no natural energy sources beyond the brilliant but intermittent gift of unfiltered sunlight. Imagine particles so small they behave like liquid, yet sharp enough to slice through metal seals with microscopic precision. So electrically charged, they leap from surfaces like living organisms, yet so persistent they penetrate every mechanical joint and electronic component with relentless determination. Lunar regolith represents one of the most insidious threats to human survival on the moon, combining the cutting power of industrial abrasives with the persistence of the finest powder and the electrical properties of materials that seem almost alive in their ability to interfere with essential equipment. These particles formed through billions of years of meteorite bombardment that shattered solid rock into fragments measuring from large boulders down to pieces smaller than the wavelength of visible light. Unlike terrestrial dust that becomes rounded and smooth through wind and water erosion, lunar dust particles maintain the sharp, angular edges created by impact fracturing. Each grain resembles a microscopic shard of glass with cutting edges that never dull through natural weathering processes. The electrostatic properties of lunar dust arise from solar wind bombardment and cosmic ray interactions that create electrical charge imbalances within individual particles and across the regolith surface. During lunar day, photoemission effects cause dust particles to acquire positive electrical charges, while areas in shadow develop negative charges that create electrical potential differences. These charge gradients cause dust particles to migrate across surfaces and leap into the air despite the absence of atmospheric circulation. Dust adhesion mechanisms operate through multiple physical forces that combine to create tenacious bonds between particles and any surface they contact. Electrostatic attraction provides the primary adhesive force, while van der Waals forces create additional molecular scale bonding between dust particles and material surfaces. The angular shape of dust grains creates mechanical interlocking that prevents easy removal through simple brushing or shaking actions. Respiratory hazards from dust inhalation represent immediate threats to human health that can cause permanent lung damage within hours of exposure to even small quantities of lunar particles. The microscopic size and sharp edges of dust grains create cutting action within lung tissue that causes inflammation, scarring, and progressive respiratory failure, similar to silicosis, but potentially more severe due to the extreme sharpness of lunar particles. Equipment contamination occurs when dust particles penetrate seals, bearings, and electronic components, where they cause mechanical wear, electrical short circuits, and thermal problems that can lead to complete system failures. Moving parts experience accelerated wear as dust acts like grinding compound between mechanical surfaces, while electrical components suffer from conductive contamination and abrasive damage to sensitive circuits. Dust mitigation strategies must address both prevention of contamination and removal of particles that have already accumulated on equipment and surfaces. Prevention involves creating physical barriers, managing electrostatic charges, and minimizing activities that disturb surface materials. Removal techniques include mechanical brushing, air blowing using pressurized gas supplies, and electrical discharge methods that neutralize electrostatic adhesion. Protective equipment modification helps shield critical systems from dust contamination while maintaining operational functionality required for survival activities. Sealing joints with available materials, creating dust covers from fabric or plastic components, and establishing clean zones where sensitive equipment can be operated provide protection against ongoing contamination. These modifications require balancing protection effectiveness against operational accessibility. Air filtration systems become essential for maintaining breathable atmosphere quality while removing dust particles that inevitably enter habitat areas despite prevention efforts. Improvised filters using fabric materials, electronic component filters, or layered screening systems help capture airborne particles before they reach life support system intakes or human respiratory passages. Filter maintenance and replacement require ongoing attention to prevent system clogging. Cleaning protocols establish systematic approaches to dust removal that minimize redistribution while effectively reducing contamination levels on critical surfaces. Dry brushing techniques help dislodge loose particles, while slightly damp cleaning methods can capture particles more effectively than dry approaches. However, water-based cleaning must account for freezing conditions and limited water supplies that make wet cleaning methods resource-intensive. Electrostatic discharge techniques neutralize the electrical charges that cause dust adhesion, making particle removal significantly more effective than mechanical methods alone. Creating electrical paths to ground through conductive materials helps dissipate accumulated charges, while controlled electrical discharge using available electronic components can neutralize surface charges that bind dust particles to equipment surfaces. Health monitoring for dust exposure symptoms helps identify respiratory problems before they become life-threatening, while guiding protective equipment usage and activity modifications. Early symptoms include coughing, throat irritation, and breathing difficulties that indicate particle inhalation. Progressive symptoms such as persistent cough, chest pain, and reduced breathing capacity signal more serious lung damage that requires immediate protective measures. Habitat pressurization management affects dust behavior and contamination patterns within living spaces where higher pressure levels can prevent external dust intrusion, while internal air circulation helps maintain cleaner breathing environments. Positive pressure differentials between interior and exterior environments prevent dust infiltration through small openings, though achieving adequate pressurization requires energy consumption and air supply management. Surface preparation techniques reduce dust generation during necessary activities while creating work areas with minimal contamination levels. Compacting loose regolith through mechanical pressure or chemical binding agents helps stabilize surface materials, while covering work areas with fabric or plastic sheeting prevents dust disturbance during equipment operations and maintenance activities. Equipment design considerations for dust resistance involve understanding how particle contamination affects different types of mechanical and electronic systems, while implementing protective measures that maintain functionality under contaminated conditions. Sealed bearings, gasketed joints, and filtered ventilation systems provide protection against dust intrusion, though these modifications may require improvisation using available materials. Maintenance schedules establish regular cleaning and inspection routines that prevent dust accumulation from reaching levels that cause equipment failures or health problems. Daily equipment inspection helps identify contamination problems before they cause major system failures, while scheduled cleaning activities maintain operational cleanliness levels without consuming excessive time and resources needed for other survival activities. Clothing and personal protection strategies minimize dust accumulation on garments and equipment while reducing transfer of contamination between different areas and activities. Outer garments that can be removed and cleaned help prevent dust transfer into clean areas, while protective covers for equipment reduce contamination during storage and transport. Managing clothing cleanliness becomes essential for preventing dust accumulation that might be redistributed during normal activities. Long-term health effects of dust exposure may include progressive lung disease, cardiovascular complications, and immune system impacts that develop over extended periods of continued exposure. Understanding these potential consequences helps guide protective equipment usage and risk management decisions while planning activities that might involve significant dust exposure risks. Emergency decontamination procedures provide rapid response protocols for situations where major dust exposure has occurred or when critical equipment becomes heavily contaminated. These procedures focus on immediate health protection and equipment preservation while minimizing further contamination spread. Emergency protocols help maintain essential system functionality during contamination crises. Advanced mitigation techniques might include constructing electrostatic precipitators using available electronic components to remove charged particles from air supplies, or creating ultrasonic cleaning systems that use vibration to dislodge particles from contaminated surfaces. These approaches require sophisticated improvisation, but can provide superior cleaning capabilities compared to simpler mechanical methods. In the alien landscape, where every footstep raises clouds of microscopic razors that drift silently through vacuum to contaminate essential equipment and threaten human health, dust management becomes a constant battle against an enemy that seems designed by nature to defeat human technology and biological systems through patient, persistent, microscopic warfare that transforms the very ground beneath your feet into a source of slow but potentially lethal contamination. At this moment, radio waves carrying distress signals from your lunar position travel through 384,400 kilometers of empty space at the speed of light, requiring 1.3 seconds to reach Earth, where they arrive weakened by distance and competing with countless other electromagnetic emissions from sources throughout the solar system. Your ability to establish communication with potential rescue operations depends on understanding the physics of radio propagation, the limitations of available equipment, and the orbital mechanics that determine when Earth-based receivers can detect signals transmitted from your location. Communication challenges begin with the fundamental problem of electrical power required to transmit signals across interplanetary distances with sufficient strength to be detected above background noise. Radio transmission power requirements increase with the square of distance, meaning that lunar-to-Earth communication requires significantly more power than typical terrestrial radio systems. Your available power sources limit transmission strength and duration, making signal efficiency and timing critical factors in successful communication attempts. Line-of-sight requirements for radio communication mean that Earth must be visible above the lunar horizon for direct signal transmission to occur. The Moon's rotation brings different areas into Earth-facing positions throughout the 28-day lunar cycle, but any given location maintains Earth visibility for approximately 14 days before rotation carries it to the far side, where direct communication becomes impossible. Understanding your position relative to Earth's location helps optimize communication timing. Radio frequency selection affects signal propagation characteristics and compatibility with Earth-based receiving equipment that might detect emergency transmissions. Higher frequencies provide better signal focusing and less atmospheric interference, but require more power and more precise antenna alignment. Lower frequencies propagate more efficiently over long distances, but may experience more interference from natural and artificial sources on Earth. Emergency communication protocols, developed by space agencies, provide standardized procedures and frequencies that rescue coordination centers monitor continuously. These protocols specify signal formats, transmission schedules, and emergency codes that help distinguish distress signals from other radio traffic. Following established emergency procedures increases the probability that transmitted signals will be recognized and responded to appropriately. Improvised antenna systems can be constructed from available metallic materials to improve signal transmission and reception capabilities beyond what portable radio equipment alone can achieve. Wire antennas fashioned from electrical cables, metal framework components, or conductive materials from damaged spacecraft can significantly improve communication range and signal clarity when properly configured for specific radio frequencies. Signal modulation techniques affect the efficiency and detectability of transmitted information while managing power consumption and transmission duration requirements. Morse code transmission requires minimal power and can be detected under poor signal conditions that would prevent voice communication. Digital data transmission can convey more information per transmission, but requires more sophisticated equipment and power resources. Visual signaling methods provide alternative communication approaches that utilize reflected sunlight or artificial light sources to create signals detectable by orbital reconnaissance satellites or Earth-based telescopes. Heliograph techniques using mirrors or polished metal surfaces can create light flashes visible across interplanetary distances when properly aimed and timed. These optical signals require no electrical power but depend on solar illumination and precise aiming. Timing considerations affect communication success because Earth's rotation and orbital motion change the orientation of receiving antennas and create predictable windows when signal reception conditions are optimal. Understanding time zones and radio propagation patterns helps schedule transmission attempts during periods when Earth-based monitoring stations are most likely to detect weak signals from lunar distances. Emergency beacon construction involves creating automated distress transmitters that broadcast continuously or on predetermined schedules to maximize detection opportunities while managing limited power supplies. Simple beacon circuits can be improvised from available electronic components to transmit identification codes and location information that help rescue operations locate your position even when you cannot actively operate communication equipment. Repeater strategies utilize natural and artificial signal reflection to extend communication range or reach Earth-based receivers when direct transmission paths are blocked or insufficient. The moon's surface can reflect radio signals to reach different parts of Earth, while artificial satellites in Earth orbit might relay weak signals that cannot be detected directly. Understanding signal reflection principles helps optimize transmission strategies. Error correction and signal verification techniques help ensure that critical information is received accurately, despite signal distortion and interference that affect long-distance radio communication. Repeating essential information multiple times, using phonetic alphabets for voice transmission, and including verification codes helps prevent miscommunication that could misdirect rescue efforts or convey incorrect survival status information. Power conservation for communication systems requires balancing transmission effectiveness against battery life while maintaining capability for ongoing communication attempts over extended periods. Scheduled transmission windows conserve power while ensuring regular contact opportunities, while emergency power reserves provide communication capability during critical situations when continuous operation becomes necessary. Directional transmission techniques focus radio signal energy toward Earth's location rather than broadcasting uniformly in all directions, improving signal strength at the receiving location while reducing power requirements for effective communication. Antenna orientation and signal focusing help maximize communication effectiveness while working within power limitations imposed by survival conditions and available equipment. Message prioritization ensures that critical information is transmitted first during brief communication windows when power or equipment limitations restrict transmission duration. Medical emergencies, location coordinates, and resource status represent priority information that should be communicated before less critical details. Establishing message priorities helps make effective use of limited communication opportunities. Multi-frequency transmission provides backup communication channels that improve the probability of successful signal reception when primary frequencies experience interference or propagation problems. Using different frequencies for repeated transmissions increases the likelihood that at least one signal will reach Earth-based receivers under varying atmospheric and electromagnetic conditions. Communication security considerations involve preventing unauthorized interception while ensuring that legitimate rescue operations can access transmitted information. Simple encryption or code systems help protect sensitive information while still allowing emergency responders to understand critical survival status and location data. However, overly complex security measures might prevent rescue operations from understanding transmitted information. Equipment maintenance for communication systems requires protecting sensitive electronic components from dust contamination, temperature extremes, and mechanical damage while maintaining operational capability throughout extended survival periods. Regular equipment inspection and cleaning help prevent communication system failures during critical periods when contact with rescue operations becomes essential. Alternative communication methods might include launching physical messages using improvised rocket systems, creating large-scale surface markings visible from orbit, or using laser pointers or other focused light sources to create detectable signals. These approaches require significant energy or materials, but might provide communication options when radio systems fail or prove inadequate. Long-term communication planning establishes sustainable schedules for ongoing contact attempts while managing resource consumption and equipment wear throughout extended survival periods. Regular communication schedules help rescue operations track survival status and plan response missions while demonstrating continued survival that maintains search and rescue priority for your situation. Advanced signal processing techniques using available electronic components might enable more sophisticated communication capabilities through digital signal processing, signal compression, or adaptive transmission methods that optimize communication effectiveness under changing conditions. These approaches require technical expertise, but could significantly improve communication success rates. In the vast emptiness between worlds, where electromagnetic radiation carries the only possible connection between a stranded survivor and distant rescue operations, successful communication becomes an exercise in physics, engineering, and determination that transforms radio waves into lifelines spanning the gulf between lunar isolation and Earth-based salvation through the fundamental forces that connect all matter and energy in the universe. Your body becomes both patient and physician in an environment where the nearest medical facility lies 384,000 kilometers away, accessible only through rescue missions that may require weeks or months to organize and execute. Every symptom demands interpretation through your own observations. Every treatment decision rests on your limited medical knowledge, and every injury or illness must be managed using improvised techniques and whatever medical supplies survived your unplanned lunar landing. Understanding basic human physiology helps distinguish between minor problems that can be managed safely and serious conditions that require immediate aggressive treatment to prevent life-threatening complications. The reduced gravity environment affects circulation patterns, bone loading, and muscle function in ways that change both injury patterns and treatment requirements compared to terrestrial medicine. Knowledge of how your body responds to lunar conditions guides appropriate treatment approaches. Wound management becomes critical because even minor cuts can become infected in the contaminated environment of damaged spacecraft and lunar dust exposure. Cleaning wounds using available water supplies and antiseptic materials prevents bacterial growth that could lead to systemic infections. However, water scarcity may require using minimal quantities for wound cleaning while still achieving adequate decontamination of injured tissues. Pressure suit emergencies represent unique medical challenges that combine trauma treatment with equipment repair under extreme time pressure. Suit punctures can cause rapid depressurization that leads to decompression sickness, hypoxia, and thermal injuries from exposure to vacuum conditions. Emergency suit repair techniques using available materials can prevent life-threatening exposure while allowing time for more comprehensive medical treatment. Low-gravity injuries often involve different mechanisms than terrestrial accidents due to altered movement patterns and reduced gravitational forces that affect how the body responds to impacts and falls. Joint strains and muscle injuries may develop gradually as the body adapts to unfamiliar movement requirements, while impacts that would be minor on Earth might cause different injury patterns due to changed momentum and force distribution. Pain management without pharmaceutical supplies requires understanding non-drug approaches that can provide relief while maintaining cognitive function needed for survival decision-making. Cold therapy using available materials helps reduce inflammation and pain from injuries, while pressure point techniques and positioning strategies can alleviate discomfort from various conditions. However, pain also provides important diagnostic information that should not be completely eliminated. Infection prevention becomes paramount because bacterial infections can become life-threatening without access to antibiotics or advanced medical intervention. Maintaining hygiene using limited water supplies, protecting wounds from contamination, and monitoring for early signs of infection help prevent minor problems from becoming major medical emergencies. Understanding infection progression guides appropriate response timing. Cardiovascular emergencies, such as heart attacks or severe arrhythmias, require immediate recognition and treatment using basic life support techniques adapted for lunar conditions. CPR effectiveness changes in reduced gravity environments where chest compression dynamics differ from terrestrial applications. Understanding how to modify standard emergency procedures for lunar conditions can mean the difference between successful resuscitation and preventable death. Respiratory problems may result from dust inhalation, equipment malfunctions, or stress responses that affect breathing patterns and lung function. Recognizing signs of respiratory distress and implementing appropriate interventions using available equipment helps maintain adequate oxygen exchange and prevent respiratory failure. However, treatment options may be limited by life support system constraints and medication availability. Bone injuries present particular challenges in reduced gravity, where fractures may have different healing patterns and mobility requirements than terrestrial expectations. Improvised splinting techniques using available materials help stabilize fractures while preventing further injury from necessary survival activities. Understanding how to create effective immobilization without interfering with essential functions requires creative problem solving. Mental health management addresses the psychological stresses of isolation, survival threats, and uncertainty that can significantly impact decision-making capability and overall survival prospects. Depression, anxiety, and cognitive impairment from stress can interfere with essential survival activities and medical self-care. Developing coping strategies and maintaining mental health becomes as important as managing physical injuries. Medication management involves making maximum use of any pharmaceutical supplies while understanding drug interactions, expiration effects, and dosage modifications that might be necessary under survival conditions. Some medications may lose potency or become dangerous under extreme temperature conditions, while others might have interactions with stress responses or altered physiology in reduced gravity environments. Dehydration and electrolyte management requires understanding fluid balance and mineral requirements while working within strict water rationing constraints. Signs of dehydration may be subtle in lunar conditions where normal thirst mechanisms and circulatory responses are altered by environmental factors. Maintaining adequate hydration without depleting water supplies requires careful balance between medical needs and resource conservation. Hypothermia and hyperthermia treatment protocols must account for the extreme temperature variations of the lunar environment while managing limited thermoregulation resources. Recognizing early symptoms of temperature-related illnesses allows intervention before they become life-threatening, but treatment options may be constrained by power consumption and equipment limitations of portable life support systems. Improvised medical equipment construction involves creating diagnostic and treatment tools, using available materials to address medical needs that exceed the capabilities of basic first aid supplies. Simple stethoscopes, thermometers, and diagnostic instruments can be constructed from electronic components and available materials to improve medical assessment capabilities when commercial medical devices are unavailable. Emergency surgical procedures may become necessary for severe injuries that would otherwise prove fatal without intervention. Understanding basic wound closure techniques, hemorrhage control, and tissue management helps address traumatic injuries using available materials and improvised instruments. However, surgical interventions carry significant risks without proper instruments and sterile conditions. Dental emergencies can cause severe pain and interfere with eating or speaking, creating additional survival challenges that affect nutrition and communication capabilities. Basic dental care, using available materials, helps manage tooth pain, gum problems, and oral injuries while preventing complications that could affect overall health and survival effectiveness. Diagnostic techniques using observation and simple tests help identify medical conditions and monitor treatment effectiveness when sophisticated medical equipment is unavailable. Taking vital signs using improvised methods, observing symptom progression, and understanding physical examination techniques provide information needed for appropriate treatment decisions. Treatment documentation involves recording medical observations, treatment attempts, and patient responses to guide ongoing care decisions while creating records that might be useful for rescue medical teams. Medical logs help track treatment effectiveness and identify patterns that might not be obvious from individual observations, while also providing valuable information for future medical support. Preventive medicine strategies focus on avoiding injuries and illnesses rather than treating problems after they develop. Understanding risk factors for common lunar environment medical problems helps guide behavior modifications and safety practices that reduce the likelihood of medical emergencies when treatment options are severely limited. Long-term health monitoring addresses ongoing health needs throughout extended survival periods while managing limited medical supplies and treatment options. Regular health assessments help identify developing problems before they become critical, while maintenance of basic health practices supports overall survival effectiveness and resistance to environmental stressors. Advanced treatment techniques might include using available electronic equipment for electrical stimulation therapy, creating controlled environmental conditions for healing acceleration, or developing specialized treatment approaches that take advantage of lunar environmental characteristics for therapeutic benefit. In the isolation of the lunar landscape, where every medical decision carries potentially life or death consequences, and every symptom must be interpreted without professional consultation, successful medical self-care requires transforming limited knowledge and improvised resources into effective healthcare through careful observation, conservative treatment approaches, and the understanding that prevention represents the most effective medical intervention when advanced treatment options lie beyond the reach of interplanetary distance and resource limitations. Food transforms from a source of pleasure and cultural expression into pure survival mathematics, where every calorie consumed must justify its contribution to maintaining life, and every nutrient becomes precious currency in the biological economy that keeps human metabolism functioning under extreme stress conditions. Your survival depends not just on having enough food to prevent starvation, but on understanding how nutritional requirements change in the lunar environment while managing limited supplies with the precision of a pharmacist measuring life-saving medications. Caloric requirements increase significantly under survival stress, despite the reduced energy demands of low-gravity movement, as your body responds to constant threat awareness, temperature regulation challenges, and healing from environmental stresses. The average adult requires approximately 2,000 calories per day under normal conditions, but survival scenarios can increase this requirement to 3,000 calories or more due to elevated metabolic rates from stress responses and immune system activation. Protein becomes particularly critical for maintaining muscle mass and immune function while your body adapts to reduced gravity conditions that alter normal muscle loading patterns and bone density maintenance requirements. Without adequate protein intake, muscle wasting accelerates beyond normal disuse atrophy, while immune system compromises increase vulnerability to infections that could prove fatal without medical intervention. Understanding protein priorities helps allocate limited food supplies effectively. Vitamin and mineral deficiencies develop more rapidly under survival stress as increased metabolic demands deplete stored nutrients, while absorption may be impaired by digestive stress responses and altered eating patterns. Vitamin C deficiency can develop within weeks without fresh sources, leading to scurvy symptoms that impair wound healing and immune function. Electrolyte imbalances from stress and altered fluid intake affect cardiac function and cognitive performance. Food preservation in the lunar environment requires understanding how extreme temperature variations, vacuum conditions, and radiation exposure affect food spoilage processes and storage requirements. Frozen foods remain preserved indefinitely in permanently shadowed areas, while foods exposed to solar heating may undergo rapid deterioration. Vacuum conditions prevent bacterial growth, but may cause moisture loss that affects texture and palatability. Rationing strategies must balance immediate nutritional needs against uncertain survival duration while maintaining morale and cognitive function that depend partially on adequate nutrition. Severe caloric restriction can extend food supply duration but may impair decision-making capabilities and physical performance needed for essential survival activities. Finding optimal rationing levels requires calculating survival probability scenarios against food availability. Psychological aspects of food consumption become significant factors in maintaining mental health and motivation during extended survival periods, when food represents one of the few remaining sources of comfort and normalcy. The psychological benefits of familiar tastes and eating rituals may justify allocating slightly larger food portions if they significantly improve mental state and decision-making effectiveness. Emergency food sources might be available from unexpected locations within damaged spacecraft systems, including emergency rations in escape pods, food supplies intended for longer missions, or edible materials used in spacecraft construction. Understanding spacecraft design and supply storage locations helps identify additional food sources that might not be immediately obvious during initial survival assessments. Digestive efficiency optimization helps extract maximum nutritional value from limited food supplies while managing digestive stress responses that can impair nutrient absorption. Eating smaller, more frequent meals improves absorption efficiency compared to large meals that may overwhelm digestive capacity under stress conditions. Chewing food thoroughly and eating slowly maximizes nutrient extraction from each portion consumed. Water content management in food affects overall fluid balance while managing precious water supplies that serve multiple survival functions. High water content foods contribute to hydration requirements, but may provide lower caloric density per unit weight. Balancing food water content against pure water conservation helps optimize total resource utilization for maximum survival benefit. Cooking and food preparation using available energy sources can improve palatability, digestibility, and safety of food supplies while managing limited fuel resources for heating. Some foods provide better nutritional value when cooked, while others lose nutrients during heating processes. Understanding optimal preparation methods helps maximize nutritional benefit while minimizing energy consumption for food preparation. Meal planning and scheduling helps maintain regular eating patterns that support metabolic stability while managing food allocation throughout uncertain survival timeframes. Regular meal times help maintain circadian rhythms and psychological normalcy, while planned menus prevent impulsive food consumption that might deplete supplies too rapidly. However, rigid scheduling must be balanced against changing survival priorities. Food safety protocols prevent foodborne illnesses that could prove fatal without medical intervention, while managing limited supplies that might be past expiration dates or stored under compromised conditions. Understanding signs of food spoilage and contamination helps prevent consumption of dangerous food while avoiding unnecessary waste of potentially safe supplies. Nutritional supplementation using any available vitamins or supplements helps prevent deficiency diseases while addressing increased nutritional demands under survival stress. Multivitamins, electrolyte supplements, or specific nutrients might be available from medical supplies or personal items that can help maintain nutritional balance when food variety is severely limited. Appetite management addresses both loss of appetite from stress and psychological eating responses that might lead to overconsumption of limited supplies. Stress can suppress normal hunger signals, leading to inadequate food intake, while anxiety about food scarcity might trigger overeating when food is available. Understanding these psychological factors helps maintain rational food consumption patterns. Food allocation strategies for group survival scenarios must balance individual nutritional needs against collective resource management while maintaining group morale and preventing conflicts over food distribution. Different individuals have varying caloric requirements based on body size, activity levels, and metabolic rates, but unequal distribution might create psychological tensions that affect group cooperation. Creative food preparation techniques using limited ingredients and cooking methods help maintain variety and palatability that support continued food consumption when appetite becomes compromised by stress or boredom. Simple seasoning from available materials, different preparation methods, or creative combinations of available foods help maintain interest in eating when psychological food aversion develops. Scavenging protocols help identify additional food sources from damaged spacecraft systems, emergency supplies, or materials that might have nutritional value despite not being intended as food. Understanding which materials might be safely consumed during desperate circumstances provides options when primary food supplies become insufficient for continued survival. Body weight and condition monitoring helps assess nutritional status and adjust food allocation strategies based on observed changes in physical condition and performance capabilities. Regular weight measurements using available scales or simple body condition assessments guide food rationing decisions while identifying when nutritional interventions become critically necessary. Hunting and foraging opportunities are virtually non-existent in the lunar environment, making food supply management entirely dependent on available stored supplies and any materials that might be repurposed for nutritional value. This limitation makes food conservation and efficient utilization absolutely critical for survival compared to terrestrial scenarios where additional food sources might be obtained from the environment. Long-term nutrition planning addresses nutritional requirements over extended survival periods while managing storage, preservation, and allocation of food supplies that must sustain life until rescue operations can be completed. Understanding minimum nutritional requirements for extended survival helps establish sustainable consumption patterns that maintain health without depleting supplies prematurely. Advanced nutrition techniques might include sprouting seeds if available, fermenting foods to improve digestibility and nutritional value, or creating concentrated nutrition solutions that maximize caloric and nutrient density per unit volume. These approaches require specific materials and knowledge, but can significantly improve nutritional outcomes when implemented successfully. In the harsh lunar environment, where every meal might represent your last opportunity to provide your body with essential nutrients for survival, food consumption becomes a carefully calculated balance between immediate physiological needs and long-term resource conservation, transforming eating from an automatic biological function into a strategic survival decision that requires understanding both human nutritional requirements and the mathematics of resource management in an environment where no additional food sources exist beyond what can be recovered from the wreckage of human ambition scattered across the ancient lunar landscape. How long can human determination sustain itself against the mathematical certainty of diminishing resources, while rescue missions traverse the vast emptiness between Earth and your lunar position at velocities that seem agonizingly slow when measured against survival timelines? The journey home begins not with the arrival of rescue spacecraft, but with understanding the complex logistics of interplanetary rescue operations, while managing your own resources and expectations throughout waiting periods that may extend far beyond initial optimistic estimates. Rescue mission planning requires months of preparation time that includes spacecraft preparation, crew training, trajectory calculations, and resource loading for missions that must account for both outbound travel to your location and return journey with additional passengers and life support requirements. Even emergency rescue missions require minimum preparation times measured in weeks rather than days, while complex rescue scenarios may require many months of preparation before launch becomes possible. Launch windows for Earth-Moon travel occur at specific intervals determined by orbital mechanics and fuel efficiency requirements that limit when rescue missions can depart Earth with reasonable chances of success. These launch opportunities may occur only every few days or weeks, depending on desired trajectory efficiency and spacecraft capabilities, meaning that rescue timeline estimates must account for orbital mechanics constraints beyond simple preparation time requirements. Travel time for rescue missions varies significantly based on spacecraft design, fuel availability, and trajectory selection that balances speed against fuel efficiency and cargo capacity requirements. Fast trajectory options might reach lunar orbit within 3 to 5 days, but require more fuel and provide less cargo capacity for rescue supplies and equipment. Slower, more efficient trajectories might require 7 to 10 days, but allow greater resource allocation for rescue operations. Communication with rescue operations helps coordinate landing site preparation, resource management, and survival timeline extensions, while providing rescue teams with essential information about your condition, location, and available resources. Regular communication schedules allow rescue planners to adjust mission parameters based on your survival status, while providing psychological support that helps maintain morale during extended waiting periods. Landing zone preparation involves creating safe touchdown areas for rescue spacecraft, while providing navigation aids that help incoming pilots locate your position accurately and land safely near your survival location. Clearing debris, marking landing boundaries, and providing visual or radio guidance signals help ensure successful rescue mission completion, while preventing landing accidents that could jeopardize both rescue and survival operations. Resource timeline calculations help determine maximum survival duration, using available supplies while identifying critical resource depletion dates that establish deadlines for rescue mission arrival. These calculations must account for consumption rate variations due to changing environmental conditions, activity levels, and resource conservation measures that might extend survival duration beyond initial estimates. Backup survival plans prepare for scenarios where primary rescue missions fail, experience delays, or prove inadequate for successful evacuation, while maintaining survival capability throughout extended periods beyond initial rescue timeline estimates. Secondary resource conservation measures, alternative shelter arrangements, and emergency protocols help maintain survival options when rescue operations encounter unexpected complications. Psychological preparation for extended isolation helps maintain mental stability and decision-making capability throughout waiting periods that may significantly exceed initial rescue timeline. Estimates while managing uncertainty about rescue mission success and arrival schedules, developing coping strategies, maintaining structured daily routines, and establishing psychological landmarks help preserve mental health during extended survival periods. Medical preparation for rescue arrival includes managing ongoing health issues while preparing for medical evaluation and possible medical intervention that rescue missions might provide upon arrival, maintaining detailed medical logs, preparing for medical questioning, and managing any medical conditions that might affect rescue operations help ensure smooth transition from survival conditions to rescue evacuation. Signal coordination with incoming rescue missions helps guide final approach and landing operations, while ensuring that rescue crews can locate your position and assess local conditions before attempting landing or resource transfer operations. Establishing communication protocols, preparing visual signals, and understanding rescue mission communication capabilities help coordinate final rescue operations. Evacuation preparation involves organizing personal effects, survival equipment, and any materials that might be valuable for post-rescue analysis, while preparing for departure from lunar surface aboard rescue spacecraft. Weight and volume limitations may restrict what materials can be transported during rescue evacuation, requiring difficult decisions about what to preserve and what to abandon. Rescue mission logistics affect spacecraft capabilities, crew resources, and mission duration that determine how rescue operations can be conducted while managing fuel reserves needed for Earth return journey. Understanding rescue mission constraints helps establish realistic expectations while preparing for rescue procedures that balance efficiency against safety requirements for all personnel involved. Emergency contingencies prepare for rescue mission problems such as spacecraft malfunctions, crew injuries, or resource shortages that might affect rescue capability while requiring additional survival duration beyond planned rescue timelines. Maintaining emergency reserves, preparing backup communication methods, and understanding contingency procedures help manage rescue mission complications. Documentation preservation involves maintaining survival logs, equipment records, and scientific observations that provide valuable information for future lunar operations while preserving evidence of survival techniques and lessons learned during emergency operations. These records might prove essential for improving future lunar mission safety and emergency response capabilities. Physical conditioning for rescue evacuation helps maintain physical capability needed for rescue operations while managing health deterioration that might occur during extended survival periods in challenging environmental conditions. Maintaining muscle strength, cardiovascular fitness, and coordination helps ensure successful participation in rescue evacuation procedures. Extraction procedures vary significantly based on rescue mission design, spacecraft capabilities, and local conditions that affect how rescue operations can be conducted safely and efficiently. Understanding possible rescue scenarios helps prepare for different evacuation methods while maintaining flexibility to accommodate rescue mission requirements and local environmental factors. Recovery expectations help prepare for post-rescue medical evaluation, debriefing procedures, and readjustment challenges associated with returning to normal environmental conditions after extended survival in extreme conditions. Managing expectations about recovery timeline and adjustment difficulties helps maintain realistic perspectives about post-rescue experiences. Mission analysis opportunities arise from survival experiences that provide valuable information for improving future lunar operations, emergency procedures, and spacecraft design requirements based on real-world survival challenges and successful improvisation techniques. Understanding the broader value of survival experiences helps maintain perspective on the significance of successful survival and rescue operations. Long-term survival scenarios prepare for possibilities that rescue missions might be delayed indefinitely or prove impossible due to technical, financial, or political constraints that affect rescue mission feasibility while requiring indefinite survival capability using available resources. Developing sustainable survival practices helps maintain life support capability for extended periods beyond normal rescue timeline expectations. Alternative rescue opportunities might arise from sources other than primary rescue missions, including commercial spaceflight operations, international rescue efforts, or lunar-based development programs that could provide rescue capability through alternative channels. Understanding diverse rescue possibilities helps maintain hope while preparing for rescue operations that might differ significantly from initial expectations. Post-rescue integration involves readjusting to normal environmental conditions, social interactions, and daily routines after extended periods of isolation and survival stress, while managing psychological and physical effects of survival experiences. Preparing for readjustment challenges helps maintain realistic expectations about post-rescue recovery and integration processes. In the silence of the lunar landscape, where Earth appears as a distant blue jewel, suspended in star-filled blackness, the way home becomes not just a matter of transportation logistics, but a complex exercise in resource management, psychological endurance, and faith in human capability to bridge the vast distances between worlds through technology, determination, and the fundamental drive to bring lost explorers safely back to the world where they belong, among the communities that await their return from the edge of human experience.